Right now, two numbers are tearing cosmology apart. One says the universe expands at 67 kilometers per second for every megaparsec of distance. The other insists it expands at 73. Both measurements are precise. Both refuse to budge. And the James Webb Space Telescope just made it worse. In the next 2 hours, we will journey from the afterglow of creation to galaxies that should not exist. We will visit black holes born too massive, witness dark energy that might be changing, and confront a crisis shaking everything Einstein believed. There is a crack running through everything we thought we knew. Scientists call it the Hubble tension. It sounds harmless, almost technical, but behind those two words hides a problem so severe that some physicists now call it a full-blown crisis. Here is the issue. For nearly a century, astronomers have tried to measure one number, just one. How fast is the universe expanding? It seems like a simple question. Point your telescope at distant galaxies. Watch them race away from us. Calculate their speed. Done. Except it is not done, because when scientists measure this expansion using nearby stars and galaxies, they get one answer. When they measure it using light from the very beginning of time, they get a completely different answer, and these two answers refuse to agree. The difference is not small. We are talking about a gap of nearly 9% between the two measurements. In most fields, 9% might be acceptable. In precision cosmology, it is a disaster. The instruments are too accurate. The methods are too refined. This gap should not exist. Think of it this way. Imagine you measure the height of a building using a tape measure from the ground floor. You get 300 feet. Then you measure it using satellite imagery from space. You get 327 feet. Both methods are trusted. Both have been checked thousands of times. Yet the building cannot be two heights at once. Something is wrong, either with our measurements or with reality itself. For years, astronomers hoped the tension would vanish. Better telescopes would find the error. Smarter calculations would close the gap. The universe would cooperate. It did not. Instead, with every new observation, the tension grew stronger, the measurements became more precise, and the gap remained, stubborn, unexplained, mocking every attempt to make it disappear. This brings us to the James Webb Space Telescope. Launched on Christmas Day of 2021, it promised answers. Its mirrors could see farther and sharper than any instrument before. If measurement errors caused the Hubble tension, Webb would find them. If crowded star fields confused older telescopes, Webb would cut through the confusion. Scientists held their breath. The data arrived, and the result shattered any hope of an easy solution. Webb confirmed that the older measurements were correct. The Hubble Space Telescope had not made mistakes. The stars were exactly where they appeared to be. The distances were accurate. The expansion rate calculated from the nearby universe held firm at around 73 kilometers per second per megaparsec. Meanwhile, measurements from the early universe still insisted on 67. The gap did not shrink, it solidified. Nobel Prize winner Adam Rees, who leads the team studying this problem, put it bluntly. With measurement errors ruled out, what remains is a real and exciting possibility. We have misunderstood the universe. Those words should send a shiver down your spine. This is not speculation from fringe theorists. This is a Nobel laureate saying our fundamental picture of reality might be incomplete. The Hubble tension means one of two things. Either there is new physics hiding in the fabric of space that we have never detected, or the model we use to describe the universe, from its birth to today, is flawed in ways we cannot yet see. Both possibilities are terrifying, both are thrilling, and both demand that we dig deeper into the foundations of cosmology itself. What created this tension in the first place? How do scientists even measure the expansion of something as incomprehensibly vast as the universe? And why do the methods disagree so violently? The answers lie in two separate journeys through cosmic history. One begins with pulsating stars in nearby galaxies. The other begins with the faint afterglow of the biggest explosion ever, the Big Bang itself. But the deeper we look into these methods, the stranger the universe becomes. The James Webb Space Telescope was supposed to be the peacemaker. For over a decade, cosmologists watched the Hubble tension grow. Two camps formed. One believed measurements of the nearby universe were somehow flawed. The other trusted those measurements and suspected something deeper was broken. Both sides needed better data. Webb promised to deliver. Its primary mirror spans over 21 feet across. Coated in gold, optimized for infrared light, it can resolve details invisible to any previous observatory. Where older telescopes saw blurry smudges, Webb sees individual stars burning across billions of light years. This power mattered because one possible explanation for the Hubble tension involved crowded star fields. The Hubble Space Telescope measured distances using special stars called Cepheid variables. These stars pulse with a regular rhythm. The brighter they truly are, the slower they pulse. By timing their flicker, astronomers calculate their true brightness. Comparing that to how bright they appear reveals their distance. Simple in theory, tricky in practice. Cepheids often sit in busy regions where many stars cluster together. If neighboring stars bleed light into the measurement, the Cepheid appears brighter than it really is. That would make it seem closer, and that would throw off distance calculations. Maybe, some hoped, this crowding effect explained the tension. Maybe Hubble had been fooled by stellar neighbors it could not fully resolve. If Webb looked at the same Cepheids with sharper vision and found they were actually farther away, the expansion rate would drop. The gap would close. Crisis averted. Webb looked. Webb measured. Webb delivered the verdict. The Cepheids were exactly where Hubble said they were. No hidden crowding. No systematic error. The distances matched almost perfectly, differing by less than 1%. The team examined over 1,000 Cepheid stars, spread across multiple galaxies, stretching out to 130 million light-years. Every single comparison confirmed the older data. Hubble had not been fooled. Its measurements stood firm. For those hoping the tension would evaporate, this was devastating news. The easy escape hatch slammed shut. Xiang Li, a graduate student working on the project, described the Webb data as seeing the universe in high definition for the first time. The signal became clearer, the noise fell away, and what remained was undeniable confirmation that the expansion rate measured locally really is higher than what early universe observations predict. We now face a harder question. If our measurements are correct, what is wrong with our understanding? Some scientists still search for subtle errors. Perhaps calibration issues in other parts of the distance ladder remain hidden. Perhaps unknown systematic effects distort results in ways not yet imagined. Science demands skepticism, and healthy skepticism demands continued checking. But with each check, the tension persists. Independent methods, using different types of stars, produce similar results. Entirely separate techniques involving gravitational lensing and time delays between multiple images of distant quasars also point toward the higher value. The evidence keeps stacking in one direction. Our local universe really does seem to expand faster than the standard model predicts. This finding carries enormous implications. The standard model of cosmology is not some rough sketch. It is a precision framework tested against countless observations. It explains the cosmic microwave background, the distribution of galaxies, the abundance of elements forged in the first minutes after the Big Bang. Abandoning it means rebuilding from foundations we thought were solid. Yet Webb's confirmation pushes us toward that uncomfortable threshold. The telescope did not solve the Hubble tension. It deepened it. Now, astronomers must ask what piece of the cosmic puzzle we have been missing all along. And to understand what might be missing, we must first understand the two numbers at war. Two numbers. That is all it takes to throw cosmology into chaos. 67 kilometers per second per megaparsec, 73 kilometers per second per megaparsec. They sound almost identical, They differ by less than 10%. Yet that tiny gap represents one of the most profound disagreements in modern physics. Let me explain what these numbers mean. The universe is expanding. Every moment, the space between distant galaxies stretches. The farther away a galaxy sits, the faster it appears to recede from us. This relationship follows a pattern first discovered in 1929 by Edwin Hubble. The Hubble constant captures this pattern as a single value. It tells us how much faster a galaxy moves away for every additional megaparsec of distance. A megaparsec equals roughly 3.26 million light years. That is about 19 quintillion miles. Hard to picture, but essential for mapping the cosmos. Now here is where the trouble begins. Scientists have two very different ways to measure this constant. The first method looks outward at the universe as it exists today. Astronomers observe Cepheid stars, exploding supernovae, and nearby galaxies. They build a ladder of distances, each rung calibrated against the previous one. This approach gives a Hubble constant, around 73. The second method looks backward in time to the universe as it existed almost 14 billion years ago. Instruments like the Planck satellite mapped the cosmic microwave background, the faint glow left over from when the universe first became transparent. By analyzing tiny ripples in that ancient light and feeding them into the standard model of cosmology, scientists calculate what the Hubble constant should be today. This approach gives around 67. Both methods are extraordinarily precise. Both claim uncertainties of only 1 or 2%, and both produce answers that cannot overlap within their margins of error. Statisticians measure disagreement in units called sigma. A 5 sigma discrepancy means there is only about 1 chance in 3.5 million that the difference arose by random fluke. The Hubble tension currently sits at roughly 5 sigma. In particle physics, 5 sigma marks the threshold for declaring a discovery. Here, it marks the threshold for declaring a crisis. Something must give. Either our measurements of the nearby universe contain hidden errors no one has yet found, or our model of how the early universe evolved into the present day is fundamentally incomplete. Consider the stakes. The Hubble constant connects to nearly everything in cosmology. Change it, and you change the calculated age of the universe. A higher value implies a younger cosmos. If 73 is correct, the universe might be closer to 13 billion years old rather than 13.8 billion. That might sound like a minor adjustment, but it creates problems. Some stars appear older than 13 billion years based on their chemistry. A younger universe with older stars makes no sense. The Hubble constant also affects estimates of how much dark matter and dark energy fill space. These mysterious components dominate the cosmic budget. Dark matter holds galaxies together. Dark energy drives the accelerating expansion. Altering the Hubble constant reshuffles their proportions and potentially breaks the delicate balance that makes our models work. This is why cosmologists cannot simply split the difference and call it 69. The physics does not allow compromise. Either the early universe measurements are wrong, or the late universe measurements are wrong, or the model connecting them is wrong. There is no middle ground. And as we will see, finding out which option is true requires understanding how each measurement actually works. The early universe method relies on ancient light and a model built from Einstein's equations. What exactly is that model, and why did scientists trust it so completely? Albert Einstein once added a single term to his equations. He later called it the biggest blunder of his life. A century later, that blunder might be the key to understanding everything. In 1915, Einstein completed his general theory of relativity. It described gravity not as a force pulling objects together, but as the bending of space and time around massive objects. Planets orbit stars because they follow curves in the fabric of space-time itself. It was elegant, it was revolutionary, and it had a problem. When Einstein applied his equations to the entire universe, they predicted something disturbing. The cosmos could not sit still. It had to either expand or collapse. There was no stable middle ground. This troubled Einstein deeply. In 1917, the scientific consensus held that the universe was eternal and unchanging. Stars might move, galaxies might drift, but the overall structure remained constant. An expanding or collapsing universe violated everything astronomers believed. So Einstein added a fudge factor. He called it the cosmological constant, represented by the Greek letter lambda. This constant acted as a kind of repulsive pressure woven into the fabric of space itself. It pushed outward against the inward pull of gravity. With the right value, Einstein could balance his equations and keep the universe perfectly static. Then, in 1929, Edwin Hubble measured distant galaxies and found they were all racing away from us. The universe was expanding after all. Einstein's static model crumbled. The cosmological constant, it seemed, was unnecessary. Einstein reportedly called it his greatest mistake, but here is where history takes a strange turn. In 1998, two independent teams of astronomers made a shocking discovery. They were measuring distant supernovae to track the expansion of the universe, expecting to see it slowing down as gravity pulled everything back together. Instead, they found the opposite. The expansion was speeding up. Something was pushing the universe apart. Something invisible, something powerful, and the simplest mathematical description of that something looked exactly like Einstein's abandoned cosmological constant. Scientists began calling this mysterious force dark energy. They reinstated lambda in their equations. Einstein's blunder turned out to be prophetic. Today, the cosmological constant sits at the heart of the standard model of cosmology. It represents the energy density of empty space itself. Even in perfect vacuum, this energy persists. It does not dilute as the universe expands. And it drives galaxies apart faster and faster as cosmic time unfolds. But there is a catch. When physicists try to calculate what the cosmological constant should be using quantum mechanics, they get an answer that is catastrophically wrong. Their prediction overshoots the observed value by a factor of 10 raised to the power of 120. That is 1 followed by 120 zeros. It is possibly the worst prediction in the history of science. This mismatch haunts cosmology. We can measure dark energy's effects with exquisite precision. We cannot explain where it comes from or why it has the value it does. The cosmological constant works beautifully in equations. It makes no sense in theory. And now, whispers grow louder that the cosmological constant might not be constant at all. New data from instruments mapping the cosmos suggests dark energy could be changing over time. If true, Einstein's simple lambda would need replacement with something far more complex. We are not there yet. The evidence remains tantalizing but incomplete. Still, the possibility looms. Einstein's greatest mistake might need revising yet again. But before we explore evolving dark energy, we must understand the model that made the cosmological constant necessary in the first place. Every science needs a rulebook. For cosmology, that rulebook has a name, lambda CDM. It sounds cryptic, but the meaning is straightforward. Lambda refers to the cosmological constant, the mysterious dark energy driving the universe apart. CDM stands for cold dark matter, the invisible substance holding galaxies together. Combine them with ordinary matter and the laws of general relativity, and you get a recipe that describes nearly everything we observe. Lambda CDM emerged in the late 1990s as a concordance model. Before it, cosmology was a mess of conflicting observations. Some data suggested the universe was open and would expand forever. Other data implied it might collapse. Estimates of the cosmic age disagreed wildly. Nothing fit together. Then came precision measurements. The cosmic microwave background revealed the geometry of space. Supernovae showed the expansion accelerating. Galaxy surveys mapped the clustering of matter across billions of light years. Piece by piece, these observations converged on a single picture. That picture is lambda CDM, It says the universe contains roughly 68% dark energy, 27% dark matter, and only 5% ordinary matter. The stuff we can see and touch, the atoms in your body, the stars in the sky, all of it amounts to just 5% of the total cosmic budget. This model has proven spectacularly successful. It predicts the detailed pattern of ripples in the cosmic microwave background with astonishing accuracy. It explains why galaxies cluster in filaments and walls, separated by vast voids. It accounts for the abundances of hydrogen, helium, and lithium forged in the first few minutes after the Big Bang. For over 2 decades, Lambda CDM has passed nearly every observational test thrown at it. Astronomers adjusted its parameters, refined its predictions, and watched the universe cooperate. It became the foundation of modern cosmology. Textbooks treat it as settled science. But foundations can crack. The Hubble tension is one crack. The model predicts an expansion rate of about 67 based on early universe data. Direct measurements of the nearby universe insist on 73. Lambda CDM cannot reconcile these numbers without modification. Another crack involves galaxy clustering. The model predicts how much matter should clump together over cosmic time. Some measurements suggest matter clusters slightly less than expected. This discrepancy, called the Sate tension, adds to the unease. Then came the James Webb Space Telescope. Its images of the early universe revealed galaxies that seemed too massive, too bright, and too mature for their age. Under Lambda CDM, the first few 100 million years after the Big Bang should have produced only small, faint protogalaxies. Webb found something different. Galaxies, almost as developed as the Milky Way, existed when the universe was barely a toddler. Some of these early objects have since been explained by black holes, mimicking the signatures of massive galaxies. Others remain puzzling. The standard model can stretch to accommodate surprises, but stretch it too far and it breaks. Scientists now face uncomfortable questions. Is Lambda CDM fundamentally correct but missing a minor ingredient? Or does it require major surgery? Could dark energy be evolving? Could dark matter behave differently than assumed? Could gravity itself deviate from Einstein's predictions on cosmic scales? No consensus exists yet. The model still fits most observations remarkably well, but cracks are cracks. Ignore them too long, and the whole structure risks collapse. Understanding these cracks requires understanding what Lambda CDM is built upon, and the most powerful constraint on the model comes from light older than any star. Roughly 400,000 years after the Big Bang, the universe became transparent for the first time. The light released in that moment still fills all of space. We call it the cosmic microwave background. Before this moment, the cosmos was a blinding fog. Temperatures soared so high that atoms could not form. Protons and electrons flew freely, constantly scattering photons. Light could not travel far without crashing into something. The universe glowed white-hot but remained opaque. Then expansion cooled everything down. Around 3,000 degrees, electrons finally slowed enough to join protons and form hydrogen atoms. Suddenly, photons could travel unimpeded. They streamed outward in all directions, and they have been traveling ever since. That ancient light now bathes us from every direction. 14 billion years of cosmic expansion stretched its wavelengths from visible glow into faint microwaves. Its temperature dropped to just 2.7 degrees above absolute zero, cold, dim, but still detectable. When scientists map this background radiation, they see an almost perfectly uniform glow. Almost, but not quite. Tiny fluctuations ripple across the sky. Some spots are slightly warmer, others slightly cooler. These differences amount to only about 1 part in 100,000, minuscule variations. Yet they encode the entire history of the early universe. Those ripples are fossils of density fluctuations in the primordial plasma. Regions slightly denser than average had slightly more gravity. They pulled matter inward. Regions slightly less dense let matter drift away. Over billions of years, denser regions grew into galaxies and galaxy clusters. Less dense regions became the great cosmic voids. By analyzing the pattern of hot and cold spots, cosmologists extract fundamental properties of the universe: the geometry of space, the amount of matter, the ratio of dark energy to everything else. All of it leaves fingerprints in the microwave background. The Planck satellite, operated by the European Space Agency from 2009 to 2013, mapped these fingerprints with unprecedented precision. Its data confirmed that the universe is geometrically flat. It measured the densities of dark matter, dark energy, and ordinary matter. It established the age of the cosmos at 13.8 billion years, and it calculated the Hubble constant. Using the standard lambda CDM model, Planck determined how fast the early universe should have been expanding and projected that rate forward to today. The answer came out around 67 kilometers per second per megaparsec. This value depends on the model. The cosmic microwave background does not directly measure the current expansion rate. Instead, it captures a snapshot of conditions long ago. Cosmologists use lambda CDM to evolve that snapshot forward through nearly 14 billion years of cosmic history. The final number reflects not just observations but assumptions about how the universe works. If those assumptions are correct, 67 should match what we measure locally. It does not. And that mismatch is the Hubble tension. Some researchers wonder if the early universe contained something extra: a brief burst of energy, a new type of particle, an unknown force. Anything that could have altered the expansion rate before the microwave background formed would change the projection. The model would spit out a different number. This idea, called early dark energy, haunts theoretical discussions. We will explore it later. For now, understand that the cosmic microwave background is both our greatest tool and our deepest puzzle. It tells us what the universe looked like in infancy. It cannot tell us if our model of cosmic adolescence is wrong. And to check that model, we need other methods. Methods that measure the universe as it exists right now. From space, the Planck satellite stared at the oldest light in existence. What it found should have settled cosmology forever. Instead, it sparked a crisis. Launched in 2009, Planck orbited a point in space about 1 million miles from Earth. There, shielded from our planet's heat and the glare of the nearby star, it scanned the entire sky repeatedly for over 4 years. Its instruments measured microwaves with exquisite sensitivity. Temperature differences of just a few millionths of a degree stood out clearly. The mission produced the most detailed map of the cosmic microwave background ever made. Where previous satellites saw broad patterns, Planck resolved fine details. It captured acoustic peaks, subtle signatures of sound waves that rippled through the early universe before atoms formed. These peaks encode precise information about cosmic parameters. Analyzing those peaks requires sophisticated modeling. Scientists feed the data into codes that simulate how the universe evolves under lambda CDM assumptions. The codes adjust parameters until simulated patterns match observed patterns. When the fit converges, the parameters reveal the state of the cosmos. Planck's final results, published in 2018, pinned down these parameters with remarkable precision. Most uncertainties shrank below 1%. The universe emerged as 68% dark energy, 27% dark matter, 5% ordinary matter. Its geometry was flat to within 0.5%. Its age stood at 13.8 billion years. And its Hubble constant came out at 67.4 kilometers per second per megaparsec, give or take less than 1%. This number created the crisis. Telescopes measuring the local universe consistently found values around 73. The gap exceeded what either measurement's uncertainty could explain. Statistically, the disagreement approached 5 sigma. Random chance could not account for it. Planck scientists explored possible issues with their data. Could foreground contamination from our own galaxy skew results? They tested for it. The effect was minimal. Could instrumental errors bias measurements? They checked calibrations exhaustively. Everything held. The problem persisted through every analysis. Whether using temperature data alone or combining it with polarization measurements, the Hubble constant stayed stubbornly low. Some researchers questioned the lambda CDM model itself. Perhaps extending the model with additional parameters would shift the Hubble constant higher, adding extra neutrino species, allowing spatial curvature, introducing interactions between dark matter and dark energy. Teams explored dozens of variations. Most extensions failed. They either could not raise the Hubble constant enough or created new tensions with other observations. A few promising ideas emerged, but none achieved consensus. The simplest model still fit most data best, except for that one infuriating number. Planck's legacy is thus bittersweet. It delivered cosmological precision beyond anything previously imagined. It confirmed lambda CDM as a remarkably accurate description of the universe, and it revealed a flaw that refuses to heal. The satellite finished its mission over a decade ago. Its data continues to be reanalyzed. Every reanalysis confirms the original findings. 67 refuses to budge. Meanwhile, local measurements keep returning 73. Both sides dig in deeper. Both sides grow more confident, and the tension between them points towards something profound waiting to be discovered. To understand why local measurements insist on a higher value, we must climb the cosmic distance ladder, and the first rung begins with stars that pulse like cosmic heartbeats. In 1912, a woman named Henrietta Leavitt noticed something peculiar about certain stars. Her discovery would eventually let us measure the universe. Leavitt worked at the Harvard College Observatory, cataloging the brightness of stars in photographs. Among thousands of stars, she found a special type that varied in brightness over time. These Cepheid variables pulsed like slow heartbeats. Some brightened and dimmed every few days. Others cycled over weeks. The key breakthrough came when Leavitt compared their pulsation periods to their true luminosities. She found a tight relationship. Brighter Cepheids pulsed more slowly. Dimmer ones pulsed faster. The correlation was so reliable that knowing a Cepheid's period immediately revealed its intrinsic brightness. This relationship turned Cepheids into cosmic yardsticks. Here is why. Imagine you see two identical flashlights. One appears bright, the other dim. You know they emit the same light. The difference in apparent brightness tells you which one is farther away and by how much. Cepheids work the same way. Measure a Cepheid's pulsation period. Calculate its true brightness from the period-luminosity relation. Compare that to how bright it appears in your telescope. The difference reveals the distance. For the first time, astronomers could measure distances to objects far beyond our own galaxy. Edwin Hubble used Cepheids in the 1920s to prove that fuzzy nebulae were actually separate galaxies millions of light-years away. His work expanded the known universe by a factor of thousands overnight. Today, Cepheids remain essential. They anchor the cosmic distance ladder, a chain of methods that extends our reach from nearby stars to the farthest visible objects. Each method calibrates the next. Cepheids provide the crucial first rungs. The Hubble Space Telescope spent years observing Cepheids in galaxies that also hosted Type Ia supernovae. These supernovae are stellar explosions of remarkable consistency. They all release roughly the same amount of light. By measuring Cepheid distances to their host galaxies, astronomers calibrated how bright the supernovae truly were. Then they used that calibration to measure distances to supernovae in galaxies far too distant for Cepheids to be seen. This ladder climbing produced the local measurement of the Hubble constant, and it consistently returned values around 73. But Cepheid measurements carry challenges. These stars often reside in dusty, crowded regions. Neighboring stars can contaminate the signal. Interstellar dust can absorb and redden light. Correcting for these effects requires careful analysis. Critics of the high Hubble constant hoped these complications explained the tension. Perhaps systematic errors accumulated with distance. Perhaps the first rungs of the ladder were slightly miscalibrated, and the error magnified as astronomers climbed higher. The James Webb Space Telescope tested this hypothesis directly. Its infrared vision cuts through dust better than Hubble's visible light cameras. Its sharper resolution separates stars that older telescopes blurred together. If crowding or dust had biased Cepheid measurements, Webb would reveal it. Webb found nothing wrong. The Cepheids sat exactly where Hubble said they did. Their distances matched within tiny fractions of a percent. The calibration held firm. This confirmation was a triumph for precision astronomy. It was a disaster for anyone hoping the Hubble tension would quietly disappear. The first rungs of the ladder are solid. The problem lies somewhere else. But where? To find out, we must understand how the entire ladder works. Measuring the universe is like crossing a canyon on stepping stones. Each stone must support the next. Miss one, and the whole journey collapses. Astronomers call this chain of measurements the cosmic distance ladder. It begins with objects close enough to measure directly and extends to galaxies billions of light years away. Each rung relies on the previous one for calibration. Errors at the bottom propagate to the top. The first rung uses parallax. Hold your finger in front of your face and close one eye, then the other. Your finger appears to shift against the background. The same principle applies to nearby stars. As Earth orbits its central star, our viewpoint shifts. Nearby stars seem to wobble against more distant ones. The amount of wobble reveals the distance. Parallax works beautifully for stars within a few thousand light years. The Gaia spacecraft has measured parallax distances for over 1 billion stars in our galaxy. These measurements are geometric. They depend only on trigonometry, not on assumptions about stellar physics. But parallax fails for distant objects. The wobbles become too small to detect, so astronomers climb to the next rung, Cepheid variables. We already discussed how Cepheids work. Their period luminosity relationship lets astronomers calculate distances to galaxies tens of millions of light years away. Gaia calibrates the Cepheid scale by measuring parallax to nearby Cepheids. That calibration transfers to Cepheids in distant galaxies. Still, Cepheids fade beyond roughly 100 million light-years. To go farther, astronomers need brighter beacons. Type Ia supernovae fill that role. These explosions occur in binary star systems. A white dwarf, the dense remnant of a dead star, pulls matter from a companion. When the white dwarf gains enough mass, it detonates in a thermonuclear blast visible across billions of light-years. Remarkably, all type Ia supernovae reach nearly the same peak brightness. This makes them excellent standard candles. By observing supernovae in galaxies where Cepheids have already measured the distance, astronomers calibrate the supernova brightness scale. Then, they observe supernovae in far more distant galaxies and use that calibration to determine distances. Combined with the galaxy's redshifts, these distances yield the expansion rate. The ladder has other rungs as well. Some astronomers use red giant stars at a specific stage in their evolution. Others use brightness fluctuations across entire galaxies. Still others exploit gravitational lensing, where massive objects bend light from background quasars, creating multiple images with measurable time delays. All these methods feed into measurements of the Hubble constant. Most return values clustered around 73 when calibrated against local standards. The agreement across independent techniques strengthens confidence in the result. Yet the ladder has critics. Each rung introduces potential errors: dust absorption, crowding effects, metallicity variations in stellar populations, peculiar motions of galaxies. Any of these could systematically bias results if not properly corrected. Teams have spent decades hunting for such biases. They use ever better telescopes. They develop more sophisticated analysis methods. They cross-check using independent rungs, and they keep finding 73. The Webb confirmation of Cepheid distances closed one major loophole. Other checks continue, but the ladder appears solid. If it is wrong, the error hides exceptionally well. This leaves the alternative. The model used to predict the Hubble constant from early universe observations might itself be flawed, and the first hints of such flaws came from an unexpected direction. Within months of its first observations, the James Webb Space Telescope spotted something impossible: galaxies that had no right to exist. The standard model of cosmology predicts how quickly structures form after the Big Bang. First, tiny density fluctuations seed the growth of dark matter halos. Then gas falls into those halos and slowly collapses into stars. Small protogalaxies merge to build larger ones. Over billions of years, majestic spirals and giant ellipticals emerge. This hierarchical assembly takes time. The first few 100 million years after the Big Bang should have produced only modest clumps, faint, small, primitive collections of young stars, nothing resembling the grand galaxies we see today. Webb looked back to that era and found otherwise. In image after image, bright, massive galaxies appeared at redshifts corresponding to just 500 million years after cosmic dawn. Some contained as many stars as the Milky Way. Others showed surprisingly mature structures. All of them seemed impossibly developed for their age. One galaxy, nicknamed the Big Wheel, displayed a spiral structure similar to our own. Another contained stars that formed when the universe was barely 300 million years old. A third appeared more massive than the Milky Way, despite having billions fewer years to grow. Headlines erupted. Had Webb broken cosmology? Did these impossible galaxies prove lambda CDM was wrong? The situation proved more complicated. Follow-up observations revealed that some of these early objects were not quite what they seemed. Supermassive black holes at their centers were actively devouring surrounding gas. The intense radiation from this feeding frenzy made the galaxies appear brighter and more massive than their actual stellar content warranted. When astronomers accounted for black hole contamination, some of the most extreme cases calmed down. The galaxies were still impressive, but no longer physically impossible. Still, puzzles remain. Even after corrections, the early universe contains roughly twice as many massive galaxies as lambda CDM predicts. Something enabled stars to form faster than standard models expect. Perhaps primordial gas converted into stars more efficiently. Perhaps massive stars were more common in the early universe. Perhaps processes we do not yet understand accelerated galaxy growth. None of these explanations require abandoning the standard model entirely. They do require adjusting assumptions about star formation and black hole growth. And they raise questions about what else we might be missing. The impossible galaxies also connect to the Hubble tension. If the early universe expanded slightly faster than lambda CDM assumes, structures would have had more time to form. More time means more growth, bigger galaxies earlier, fewer impossibilities. This tantalizing link is not proof of new physics. It is a hint, a suggestion that different cracks in cosmology might share a common cause. And among the strangest hints are objects astronomers never expected to find at all. They appeared as tiny crimson specks in Webb's deepest images. Scientists called them little red dots. Nobody knows exactly what they are. Since Webb began operations, it has discovered hundreds of these objects scattered across the early universe. They share certain characteristics: small in apparent size, extremely red in color, astonishingly bright for their distance. Most existed within the first 1.5 billion years after the Big Bang. At first, astronomers assumed they were compact galaxies packed with unusually red stars. Dust absorption could redden starlight, making blue stars appear red. Heavy element enrichment could also shift stellar colors. But when teams analyzed the spectra of little red dots, they found something unexpected. Many showed signatures of gas swirling at tremendous speeds, over 2 million miles per hour. Such velocities indicate material orbiting close to a supermassive black hole. The red color might come not from stars, but from hot gas and dust surrounding actively feeding black holes. This interpretation raises its own problems. Supermassive black holes in the local universe follow a tight relationship with their host galaxies. Bigger galaxies harbor bigger black holes. The masses correlate across many orders of magnitude. Little red dots seem to violate this relationship. Their black holes appear overly massive compared to their stellar content. It is as if the black holes grew first and the galaxies lagged behind. Some researchers estimate that 70% of little red dots contain actively growing black holes. If confirmed, this implies a hidden era of intense black hole growth in the early universe, a cosmic adolescence far more turbulent than models predicted. Others remain cautious. The spectral signatures could have alternative explanations. Dust geometry might mimic black hole indicators. Selection effects could bias which objects Webb detects. The sample might not represent typical early galaxies. What seems clear is that little red dots were abundant. They popped up everywhere Webb looked, and they vanished after a certain cosmic era. By the time the universe reached 2 billion years old, little red dots became rare. Whatever they were, they represented a transient phase in cosmic evolution. This transience is itself a clue. Perhaps little red dots were galaxies caught in a brief, violent growth spurt. Perhaps their central black holes eventually merged or settled down. Perhaps dust cleared and revealed the galaxies we recognize today. Each possibility has implications for cosmology. If black holes formed and grew faster than expected, they could have influenced their surroundings in ways models currently ignore. That influence might affect how galaxies assembled and how the expansion rate evolved. The little red dots remain an open mystery. Webb continues to observe them. Spectroscopic follow-ups gather more data. Theoretical models scramble to accommodate these strange objects. But the little red dots are just one piece of a larger puzzle. Supermassive black holes themselves have posed problems long before Webb launched. 20 years ago, astronomers found something that should not exist: quasars blazing at the edge of the observable universe. Black holes billions of times more massive than our star, all of them burning brightly when the cosmos was less than 1 billion years old. The discovery defied easy explanation. Black holes form when massive stars die. They start with perhaps dozens of times the mass of our star. To grow into monsters weighing billions of stellar masses, they must consume enormous amounts of gas over long periods. But there are limits. When a black hole feeds too aggressively, the infalling material heats up and radiates intensely. That radiation pushes outward, shoving away the very gas the black hole wants to eat. This creates a speed limit called the Eddington limit. Feed faster, and the radiation blows your meal away. Given this limit, a stellar mass black hole would need billions of years to grow into a supermassive giant. Yet there they were, fully formed quasars, shining from an era when the universe was only 700 million years old. The math did not work. Theorists proposed solutions. Perhaps some black holes started bigger. Primordial gas clouds collapsing directly into black holes weighing tens of thousands of stellar masses could skip the slow growth phase. These direct collapsed black holes would have a head start. Alternatively, maybe the Eddington limit can be violated briefly. Episodic bursts of super-fast feeding might let black holes grow in spurts. Thick flows of gas could absorb radiation before it escapes, allowing continued accretion. Both ideas remain theoretical. Neither has been conclusively demonstrated. The James Webb Space Telescope has made the problem more pressing. It found actively growing black holes at even earlier times. One object, observed just 570 million years after the Big Bang, hosts a black hole far more massive than its host galaxy should allow. The black hole appears to have outgrown its home. Webb also spotted a candidate black hole that seemed to be feeding at 40 times the Eddington limit. Later analysis suggested dust had confused the initial estimates. The black hole was probably feeding normally. But the initial excitement shows how eagerly scientists seek evidence of exotic growth mechanisms. If supermassive black holes really did grow faster than standard models allow, the implications ripple outward. Black holes influence galaxy formation. Their radiation heats surrounding gas. Their jets blow material out of galaxies. Their gravity shapes the orbits of nearby stars. Getting black hole formation wrong means getting galaxy formation wrong. And getting galaxy formation wrong could mean getting the expansion history wrong. This chain of reasoning remains speculative, but it illustrates how interconnected cosmology has become. A surprise in one corner of the field tugs at assumptions everywhere else, and the biggest surprises often involve objects breaking records they should not break. Let me tell you about a galaxy that should be impossible. Its name is a string of letters and numbers that means nothing to most people. What matters is what it represents. A cosmic rebel that defies the timeline. This galaxy was observed as it existed roughly 800 million years after the Big Bang. Light left it over 13 billion years ago. When Webb captured that light, astronomers expected to see a young, chaotic system still assembling itself. Instead, they found a galaxy already containing more stars than the Milky Way. Its stellar population had formed roughly 1.5 billion years before the observation. That means the stars were born when the universe was barely 300 million years old. Pause on that for a moment. 300 million years after the beginning of everything. The universe was still an infant. Radiation still dominated over matter. The first structures had barely begun to clump together. And somehow, this galaxy was already churning out stars at a ferocious rate. Under the standard model, such early massive galaxies pose a severe challenge. Dark matter halos, the gravitational scaffolds where galaxies form, need time to grow. They start small and merge over cosmic ages into larger structures. Without sufficiently large halos, galaxies cannot accumulate enough gas to produce billions of stars. Yet there it was, a fully assembled giant in an era of supposed dwarfs. The researchers who studied this galaxy used the word significant challenge when describing its implications. They noted that if many such objects exist, our understanding of galaxy and black hole formation in the early universe requires revision. Some explanations preserve the standard model. Perhaps black hole activity mimicked stellar light, inflating mass estimates. Perhaps unusual stellar populations burned brighter than typical stars, making the galaxy appear more massive than it truly was. Other explanations venture further. Perhaps dark matter halos formed more efficiently than predicted. Perhaps early dark energy gave the universe an extra kick, accelerating structure formation. Perhaps some entirely unknown process operated in the primordial cosmos. Webb has found multiple candidates for these impossibly mature early galaxies. Not one fluke, but a pattern. Wherever the telescope looks deeply enough, surprises emerge. This does not mean lambda CDM is wrong. Models have flexibility. Parameters can be adjusted. Assumptions can be refined. But the adjustments are piling up. Each new anomaly requires another tweak. At some point, the patches may become more complicated than starting fresh. We are not at that point yet. The standard model remains the best available description of the cosmos, but it no longer feels as settled as it once did. And at the heart of these unsettling discoveries lies a process that seems to have run impossibly fast in the early universe. Stars do not form easily. Gas must cool, collapse, and compress until nuclear fusion ignites. Each step faces obstacles. Radiation pressure pushes outward. Turbulence stirs the gas. Magnetic fields resist compression. Forming stars requires overcoming all of these barriers. In the modern universe, galaxies convert roughly 10% of their available gas into stars. The rest remains scattered, too hot, or too turbulent to collapse. This efficiency has been measured in thousands of galaxies across billions of years of cosmic history. 10% is the norm. Now consider the early galaxies Webb observed. To explain their masses given the short time available, they would need to have converted nearly 100% of their gas into stars. 100%. No wasted material, no leftover gas, Every atom of hydrogen funneled into stellar furnaces with perfect efficiency. This is technically possible but wildly implausible. It would require star formation to proceed without any of the usual obstacles. No radiation feedback, no supernovae blowing gas out of galaxies, no turbulent mixing to delay collapse. In other words, it would require conditions nothing like what we see today. Some theorists propose that early star formation was indeed different. The first generation of stars, born from pristine hydrogen and helium with no heavier elements, might have been more massive on average. Massive stars are brighter. A galaxy with many massive stars would appear more luminous, potentially mimicking a larger stellar mass. Others suggest that star formation proceeded in intense bursts rather than steady flows. Short periods of extreme efficiency could produce many stars quickly before feedback shut the process down. The bursts would need to happen repeatedly, building up stellar populations in spurts. Still, others invoke black holes. Actively growing black holes emit tremendous radiation. Some of that radiation could be misidentified as starlight, inflating mass estimates. Correcting for black hole contamination might reveal that early galaxies were less massive than they first appeared. Each proposal has merits. Each has difficulties. None fully explains the observations without invoking something unusual. This is where cosmology becomes genuinely exciting. When observations resist explanation, new physics may be lurking. Not necessarily revolutionary physics, perhaps just refinements to how stars form or how we interpret light from distant objects, but possibly something deeper. The Hubble tension and the impossible early galaxies might share a common cause. If the early universe expanded faster than lambda CDM predicts, more time would have passed before the cosmic microwave background was emitted. More time means more opportunity for structure to grow. More structure means bigger galaxies earlier. This connection remains speculative. Proving it requires more than suggestive coincidences. It requires new theoretical models that make testable predictions and observations that confirm or rule out those predictions. But the possibility electrifies researchers. A single adjustment might resolve multiple puzzles simultaneously. That kind of elegance is rare and precious in science. Before we explore what such an adjustment might look like, we must understand the invisible forces that dominate the cosmos. Galaxies should not exist. At least, not the way we observe them. Their stars orbit too fast. Their disks should fly apart. Something unseen must be holding them together. We call that something dark matter. The evidence accumulated over decades. In the 1970s, astronomer Vera Rubin measured how fast stars orbit in distant galaxies. She expected stars far from galactic centers to orbit slowly. Gravity weakens with distance. Outer stars should drag behind inner ones. Instead, she found flat rotation curves. Stars at the edges orbited just as fast as stars near the center. Either Newton's laws failed at galactic scales, or invisible mass was adding extra gravitational pull. Most physicists chose the second option. Dark matter, they proposed, forms vast halos surrounding visible galaxies. It does not emit light. It does not absorb light. It interacts with ordinary matter only through gravity, but its gravitational influence is enormous. Subsequent observations supported this picture. Galaxy clusters behave as if they contain far more mass than their visible stars and gas account for. Gravitational lensing, the bending of light around massive objects, reveals dark matter distributions directly. The cosmic microwave background shows imprints that only make sense if dark matter was present in the early universe. The lambda CDM model assigns 27% of the cosmic energy budget to dark matter. That is over 5 times more than ordinary matter. By mass, dark matter dominates the material universe. Yet, we have never detected a dark matter particle directly. Experiments deep underground search for rare collisions between dark matter and ordinary atoms. So far, nothing conclusive has appeared. Particle accelerators hunt for dark matter candidates among their debris. No discoveries yet. We know dark matter exists because of its gravitational effects. We do not know what it is made of. The leading candidates are hypothetical particles called WIMPs, weakly interacting massive particles. If WIMPs exist, they would have been produced in the hot early universe and survived to the present day in vast quantities. Their weak interactions would explain why direct detection is so difficult. Other candidates include axions, extremely light particles proposed to solve unrelated problems in particle physics. Primordial black holes, formed before stars existed, have also been suggested. None of these ideas has been confirmed. This ignorance matters for cosmology. The behavior of dark matter affects how structures form. If dark matter is cold, meaning its particles move slowly, structures build from the bottom up. Small clumps merge into larger ones over time. This matches observations reasonably well. But if dark matter has unexpected properties, structures might form differently. Warm, dark matter, with faster moving particles, would smooth out small-scale clumping. Self-interacting dark matter, where particles occasionally collide with each other, could alter the density profiles of halos. Some researchers wonder if dark matter's properties might connect to the Hubble tension or the impossible early galaxies. Perhaps dark matter behaved differently in the young universe. Perhaps interactions we have not accounted for influenced early structure formation. These ideas remain speculative. Standard cold, dark matter still fits most observations, but the mysteries keep piling up. And standing beside dark matter is an even stranger phenomenon. Space itself is expanding, and something is making it expand faster and faster. We call this something dark energy. It accounts for 68% of everything in the universe. We have almost no idea what it is. The story begins with supernovae. In the late 1990s, two independent teams measured how bright distant Type Ia supernovae appeared compared to nearby ones. The goal was to track the expansion history of the universe. Everyone expected gravity to slow the expansion over time. The teams would measure how much. Instead, they found the opposite. Distant supernovae were dimmer than predicted. They were farther away than expected. Space between us and them had expanded more than gravity should have allowed. Something was pushing the universe apart. Something that grew stronger as space expanded. Something that counteracted gravity on the largest scales. Einstein's cosmological constant fit the bill perfectly. As a property of space itself, its density remains constant even as the universe expands. More space means more total dark energy, and more dark energy means faster acceleration. The lambda CDM model incorporated this idea seamlessly. Dark energy acts like a pressure woven into the fabric of space-time. It does not dilute like matter or radiation. It just exists, everywhere, pushing everything apart. But the cosmological constant has a disturbing feature. Quantum mechanics predicts that empty space should seethe with energy. Virtual particles pop in and out of existence constantly. Their collective energy should produce a cosmological constant. The prediction fails catastrophically. Calculated values overshoot observations by a factor so large it defies comprehension. 1 followed by 120 zeros. The worst mismatch in physics. Either quantum mechanics is deeply wrong about vacuum energy, or something cancels most of it out, or we misunderstand the connection between vacuum energy and gravity. No satisfactory explanation exists. And now, hints emerge that the cosmological constant might not be constant at all. The Dark Energy Spectroscopic Instrument, called DESI, has mapped nearly 15 million galaxies and quasars over 11 billion years of cosmic history. By measuring patterns in how matter clumps, DESI tracks the influence of dark energy through time. Combined with other observations, DESI data suggests dark energy might be weakening. Its influence in the early universe might have been stronger than today. If confirmed, the cosmological constant interpretation would require replacement with something more dynamic, This finding has not yet reached the threshold of discovery. Statistical uncertainties remain significant, but the hint persists across multiple data combinations, and it points toward exactly the kind of new physics that might resolve the Hubble tension. Here is a number that should disturb you. Roughly 68% of everything in the universe is dark energy, not matter, not radiation, not anything we can see or touch or detect directly, just empty space pushing itself apart. How did we arrive at this staggering conclusion? The evidence comes from multiple directions. First, the geometry of space itself. General relativity connects the total energy content of the universe to its curvature. A universe with too little energy curves in one way. Too much energy curves the opposite way. Just the right amount produces a flat universe where parallel lines stay parallel forever. Measurements of the cosmic microwave background reveal a flat universe. The total energy density must equal a critical value. But adding up all the matter, both ordinary and dark, only gets us to about 30%. The remaining 70% must come from something else. Second, the acceleration of cosmic expansion. Supernovae and other distance indicators show that the expansion rate is increasing. Only a component with negative pressure, something that pushes rather than pulls, can drive acceleration. Matter cannot do this. Radiation cannot do this. Only dark energy fits. Third, the integrated history of structure formation. Galaxies cluster in ways that depend on how much dark energy influence their growth. Surveys like DESI measure these patterns and constrain dark energy's contribution. The answer consistently comes out around 70%. Fourth, the cosmic microwave background itself. The heights and positions of acoustic peaks depend on the balance between matter, radiation, and dark energy. Fitting the observed peaks requires dark energy to dominate. All these lines of evidence converge on the same picture. Dark energy is real. It fills all of space, and it constitutes the majority of the cosmic budget. This dominance has consequences. In the distant future, dark energy will win the cosmic tug-of-war against gravity. Galaxies not already bound together will drift apart. The local group, our galaxy, and its neighbors, will remain together. Everything else will recede beyond the observable horizon. Eventually, trillions of years from now, future astronomers will see only their local cluster. The rest of the universe will have vanished into the darkness, accelerated away by relentless expansion. But that future assumes dark energy remains constant. If it changes, predictions change too. Desi's hints of evolving dark energy suggest we might not understand the fate of the cosmos. Perhaps dark energy will continue weakening until it no longer dominates. Perhaps the expansion will slow and eventually stop. Perhaps gravity will reassert itself and pull everything back together. Or perhaps dark energy will strengthen instead. In that case, the acceleration could become so extreme that it tears apart galaxies, stars, planets, atoms. This grim scenario, called the Big Rip, remains speculative but possible. We do not know which future awaits. We barely understand what dark energy is. What we do know is that the universe is stranger than anyone imagined a century ago. Einstein introduced his cosmological constant as a mathematical convenience. Today, it represents the dominant component of reality. And the more we learn about it, the more questions arise. The Hubble tension, the impossible early galaxies, the hints of evolving dark energy, all these puzzles might be connected. A single piece of missing physics could unlock multiple mysteries simultaneously. In the chapters ahead, we will explore what that missing piece might be, and we will discover just how much our understanding of reality hangs in the balance. Deep in the Arizona desert, a remarkable machine is rewriting our understanding of the cosmos. It has already mapped 15 million galaxies, and its findings hint at something extraordinary. The dark energy spectroscopic instrument, known as DESI, sits atop a mountain in the Sonoran Desert. 5,000 robotic fiber optics swivel independently, each one targeting a different galaxy or quasar. In a single night, DESI captures more spectra than previous surveys gathered in years. By measuring how light from distant objects stretches as it travels through expanding space, DESI tracks the cosmic expansion across 11 billion years of history. The patterns it detects carry imprints of dark energy's influence at different epochs. The collaboration released its latest results in early 2025. Over 900 researchers from 70 institutions analyzed the data. What they found sent ripples through the cosmology community. When DESI data stands alone, it remains consistent with the standard lambda CDM model. Dark energy could still be Einstein's cosmological constant, unchanging through time. Nothing definitive breaks. But when researchers combine DESI measurements with other observations, a different picture emerges. Data from the cosmic microwave background, distant supernovae, and gravitational lensing all get folded into the analysis. Together, these datasets struggle to fit the standard model. They prefer something else. That something else is evolving dark energy. Instead of remaining constant, dark energy's influence appears to weaken over cosmic time. It was stronger in the past. It is becoming gentler now. The statistical significance hovers between 3 and 4 sigma, depending on which datasets combine. This falls short of the 5 sigma threshold physicists demand for discovery. Many 3 sigma hints have evaporated with more data. Caution remains appropriate. Still, the persistence is striking. The first DESI data release hinted at evolution. The second release, with more than double the galaxies, strengthened the hint. Different analysis methods and different dataset combinations all point in the same direction. Will Percival, one of DESI's spokespersons, described the situation bluntly. The simplest explanation for what they observe is shifting. It looks increasingly likely that the standard model needs modification. Evolving dark energy seems promising. If confirmed, this would be revolutionary. The cosmological constant has anchored cosmology for over 2 decades. Replacing it with a dynamic field would require entirely new physics. Theorists would need to explain what drives the evolution, why it happens at this rate, and what it means for the future of the universe. Some models already exist. Quintessence, a hypothetical field that changes over time, has been studied for decades. It could produce evolving dark energy naturally. Other proposals invoke interactions between dark energy and dark matter, or modifications to gravity itself. None of these ideas has strong independent evidence yet. DESI provides motivation but not proof. More data will come. The survey aims to map 50 million objects before completion. Other experiments, including the Vera Rubin Observatory and the Euclid Space Telescope, will provide complementary measurements. Within a few years, the picture should clarify. Either evolving dark energy will solidify into discovery, or it will fade as a statistical fluctuation. The stakes could not be higher. And here is where the story becomes even more intriguing. Evolving dark energy might not just explain DESI's findings. It might also resolve the Hubble tension and explain the impossible early galaxies. A single piece of new physics solving multiple puzzles simultaneously would be extraordinarily elegant. It would signal that cosmology is on the verge of a breakthrough comparable to the discovery of cosmic acceleration itself. But before we explore that tantalizing possibility, we need to understand a specific version of evolving dark energy that has captured theorists' attention. What if the universe received an extra push right after the Big Bang? A brief surge of energy that vanished almost as quickly as it appeared. This idea, called early dark energy, might be the key that unlocks multiple cosmic mysteries at once. The concept is simple in principle. Imagine a new energy field that activated shortly after the universe began. For a few 100,000 years, it contributed significantly to the total energy budget. It sped up the expansion slightly. Then, just before the cosmic microwave background formed, it switched off. It decayed away, leaving almost no trace. This fleeting presence would have consequences. By boosting the early expansion rate, early dark energy would change how we interpret the cosmic microwave background. The Hubble constant calculated from that ancient light would shift upward. The gap between 67 and 73 might close. Researchers at MIT and other institutions recently tested this idea rigorously. They incorporated early dark energy into sophisticated simulations of cosmic evolution. They tracked how dark matter halos formed, how galaxies assembled, and how the expansion rate evolved. The results were striking. Early dark energy did more than address the Hubble tension. It also produced more massive galaxies earlier in cosmic history. The same adjustment that raised the predicted Hubble constant also explained why Webb sees surprisingly mature galaxies in the infant universe. Two puzzles, one solution. That kind of elegance makes physicists pay attention. The mechanism works through interconnected effects. Early dark energy alters several cosmological parameters simultaneously. It increases the amplitude of density fluctuations in the primordial plasma. Larger fluctuations seed larger dark matter halos. Larger halos attract more gas. More gas forms more stars. Bigger galaxies emerge faster. Meanwhile, the modified expansion history changes how distances translate into the Hubble constant. When cosmologists project from the early universe to today, using the adjusted model, they get a higher value. The tension eases. Critics raise valid concerns. Early dark energy must switch off at precisely the right moment. Too early, and it does not affect the Hubble constant enough. Too late, and it distorts the cosmic microwave background in detectable ways. The timing seems suspiciously fine-tuned. Theorists invoke particle physics to justify this timing. They propose axion-like fields that naturally evolve in the required way. The field sits frozen at high energies, contributing to dark energy. As the universe cools, it begins oscillating and rapidly dilutes away. The transition happens around the right epoch. Whether nature actually works this way remains unknown. Early dark energy is a hypothesis, not a discovery. It fits certain observations beautifully, but lacks independent confirmation. Testing it requires precise measurements from multiple experiments. The cosmic microwave background carries subtle signatures that differ between standard lambda CDM and early dark energy models. Future surveys might detect these differences. DESI's hints of evolving dark energy add intrigue. If dark energy changed recently, perhaps it also changed in the early universe. Different epochs might have experienced different flavors of cosmic acceleration. The full history could be far more dynamic than anyone imagined. This possibility excites researchers because it connects disparate phenomena. The Hubble tension, the impossible galaxies, and the evolving dark energy might all reflect the same underlying reality. A universe with a more complex energy history than the simple cosmological constant allows. But early dark energy is not the only proposed solution. Some physicists suspect that gravity itself might need revision. For over a century, general relativity has reigned supreme. Einstein's equations describe gravity with extraordinary precision. Every test, from planetary orbits to gravitational waves, confirms his theory. Yet some researchers wonder if it fails on the largest scales. The idea is not as radical as it sounds. General relativity was developed to explain gravity in the solar system. Einstein never tested it across billions of light years. He could not have imagined the observations we make today. Perhaps his equations need adjustment when applied to the entire cosmos. Modified gravity theories propose exactly this. They alter Einstein's equations in ways that only matter at cosmological distances. Locally, everything looks normal. Planets orbit as expected. Light bends around massive objects correctly. But the expansion history of the universe and the growth of cosmic structures might differ from general relativity's predictions. One class of modifications introduces new fields that couple to gravity. These fields could mimic dark energy without requiring a cosmological constant. They could also affect how matter clumps, potentially altering the relationship between early and late universe measurements. Another approach questions whether gravity weakens at extremely large scales. If gravitational attraction falls off faster than Einstein predicted, distant galaxies would accelerate away more easily. The observed cosmic acceleration might not require dark energy at all. These ideas remain speculative. Modified gravity theories must thread a narrow needle. They must reproduce all the successes of general relativity locally while producing different effects cosmologically. Most proposals fail this test. They either contradict solar system observations or require fine-tuning that feels artificial. Still, the Hubble tension motivates continued exploration. If no dark energy model can resolve the discrepancy, perhaps the problem lies with gravity itself. The model we use to connect early and late universe measurements assumes general relativity holds everywhere. Relaxing that assumption opens new possibilities. Some researchers have proposed that gravity behaves differently in the presence of dark energy. The interplay between the two could produce effects not captured by treating them separately. Such interactions might leave signatures in how galaxies cluster or how light travels across cosmic distances. Testing modified gravity requires observations that distinguish it from dark energy. Gravitational waves offer one avenue. The speed at which these ripples travel depends on the theory of gravity. General relativity predicts they move at exactly the speed of light. Some modified theories predict slight deviations. In 2017, astronomers detected gravitational waves and light from the same neutron-star collision. Both signals arrived within 2 seconds of each other after traveling 130 million light-years. This observation ruled out many modified gravity proposals. The survivors must be cleverly constructed to evade such constraints. The cosmic microwave background provides another test. Different gravity theories produce different patterns in the ancient light. Planck data already constrains modifications tightly. Future experiments will tighten these constraints further. For now, general relativity remains the best description of gravity we have. The Hubble tension might have other explanations, but the possibility that Einstein's crowning achievement needs extension on the grandest scales keeps theorists searching. And one framework that has long promised to unify gravity with quantum mechanics has struggled mightily with the very existence of dark energy. String theory was supposed to be the theory of everything. It promised to unite gravity with quantum mechanics. It described fundamental particles as tiny vibrating strings. It required extra dimensions of space. And for decades, it could not accommodate our actual universe. The problem was dark energy. String theory works most naturally in universes with negative or zero energy density. These configurations, called anti-de Sitter spaces, have well understood mathematical properties. Calculations proceed cleanly. Predictions emerge clearly. Our universe has positive energy density. Dark energy pushes it apart. This configuration, called de Sitter space, is far harder to describe in string theory. For years, no one could construct a convincing model. This failure was embarrassing. The most ambitious framework for fundamental physics could not describe the dominant component of reality. Critics pointed to this gap as evidence that string theory had lost touch with observation. Theorists worked for decades to bridge the divide. They proposed elaborate constructions involving extra dimensions stabilized by exotic fields. Some claimed success. Others found flaws in the arguments. The debate grew contentious. Then, in 2024, two physicists published a breakthrough. Bruno Bento and Miguel Montero constructed an explicit de Sitter solution in string theory. For the first time, the framework could describe a universe with positive dark energy. Their solution has unusual features. It lives in 5 dimensions rather than 4. The dark energy it describes is unstable. It will weaken over time. The universe it depicts is not quite ours. Still, the achievement matters. It demonstrates that string theory can accommodate dark energy in principle. Further work might refine the construction into something closer to observation. Intriguingly, the solution predicts evolving dark energy. This matches Desi's hints. If string theory is correct, the cosmological constant cannot be truly constant. It must change, even if slowly. This connection is speculative but tantalizing. String theory has been criticized for making no testable predictions. Evolving dark energy could change that. If observations confirm that dark energy weakens over time, string theory might finally have empirical support. The implications extend beyond theoretical physics. If string theory correctly describes dark energy, it might also explain the mysterious fine-tuning that makes the cosmological constant so small. The theory's landscape of possible universes might select for conditions compatible with observers like us. These ideas venture into philosophy as much as physics. They invoke anthropic reasoning and multiverse scenarios that many scientists find unsatisfying. But they represent genuine attempts to connect abstract mathematics with observed reality. String theory's struggle with dark energy illustrates a broader point. Our best theories of fundamental physics do not naturally produce the universe we see. Something is missing. That something might be revealed by the very tensions and anomalies that trouble cosmology today. And if dark energy really is changing, the implications for our cosmic future are profound. What happens if the force pushing the cosmos apart is losing strength? The answer depends on how quickly it fades. In the standard picture, dark energy remains constant forever. Its density never changes. As the universe expands, matter dilutes, but dark energy does not. Eventually, dark energy dominates completely. Galaxies not bound together drift apart. The cosmos grows cold, dark, and empty. This is the heat death of the universe, a slow fade into eternal stillness. But Desi's hints suggest dark energy might be weakening. If so, the future could look very different. Consider a scenario where dark energy continues declining at its current rate. Billions of years from now, its influence might become negligible. Gravity would reassert dominance. The expansion would slow, then stop, then possibly reverse. Galaxies that were racing apart would begin falling toward each other. Clusters would merge. The universe would contract. Temperatures would rise. Eventually, everything might collapse into a final singularity. A big crunch, the reverse of the Big Bang. This scenario once seemed plausible before dark energy was discovered. Now it requires dark energy to essentially disappear. Current hints suggest weakening, not vanishing. The outcome depends on details we cannot yet measure. Another possibility involves dark energy stabilizing at a lower value. The expansion would continue but decelerate. The heat death would still occur, just on different timescales. The universe would grow old more slowly. A third scenario is more exotic. What if dark energy oscillates? It might weaken for a while, then strengthen, then weaken again. The expansion rate would fluctuate over cosmic time. The universe might undergo cycles of acceleration and deceleration, never reaching a final state. Theorists have proposed all these possibilities and more. Without knowing what dark energy actually is, predicting its future behavior remains guesswork. One extreme scenario deserves mention. If dark energy strengthened instead of weakened, the consequences would be catastrophic. Acceleration would become so violent that it would tear apart the fabric of reality. Galaxy clusters would separate, then individual galaxies, then stars, then planets, then atoms. This is the Big Rip, a cosmic apocalypse where space itself expands faster than any force can resist. Current observations disfavor the Big Rip. Dark energy appears constant or weakening, not strengthening. But the uncertainties are large. Future measurements will clarify the trend. For now, we face profound uncertainty about the ultimate fate of everything. The same dark energy that dominates today might behave completely differently tomorrow. Our cosmic future hangs on physics we barely understand. This uncertainty is humbling. Humanity has existed for an eye blink of cosmic time. We have studied the universe seriously for only a few centuries. The questions we ask about dark energy and expansion rates will take generations to answer. But we are making progress. Every new observation narrows the possibilities. Every hint, including those from Deci, brings us closer to the truth. The fate of the cosmos might remain unknown today. It need not remain unknown forever. And if the standard model of cosmology is truly incomplete, the consequences extend beyond distant futures into present-day physics. Imagine waking up to discover that everything you thought you knew was mistaken. Not completely wrong, just incomplete. The rules that seemed solid turned out to be approximations. The framework that explained so much revealed hidden gaps. This is what cosmologists might soon face. The Lambda CDM model has been remarkably successful. It explains the cosmic microwave background, the distribution of galaxies, the abundances of light elements, and the accelerating expansion. For over 2 decades, it has passed nearly every test, but cracks are appearing. The Hubble tension refuses to close. Early galaxies appear too mature. Deci hints at evolving dark energy. Each anomaly alone might be explained away. Together, they suggest something deeper. If Lambda CDM is fundamentally incomplete, several implications follow. First, our estimates of the cosmic inventory might need revision. The proportions of dark matter, dark energy, and ordinary matter derive from fitting the model to observations. Change the model, and the proportions shift. The universe might contain different amounts of each component than we currently believe. Second, the age of the universe might change. The standard model gives 13.8 billion years. A higher Hubble constant implies a younger cosmos. If the tension resolves in favor of local measurements, the universe might be closer to 13 billion years old. That creates problems if some stars appear older than this revised age. Third, our understanding of structure formation might require overhaul. Lambda CDM predicts how galaxies form and cluster. If early dark energy or modified gravity alters this process, simulations would need rebuilding from scratch. Decades of work might require significant revision. Fourth, the connection between particle physics and cosmology might deepen. New components like early dark energy or interacting dark matter would require explanation in terms of fundamental particles and forces. The standard model of particle physics might need extension to accommodate whatever cosmology discovers. These implications sound dramatic. They are also exciting. Science advances when old frameworks break. The cracks in Lambda CDM might be the first signs of revolutionary discoveries. History offers precedents. Newton's gravity worked brilliantly for centuries before Einstein revealed its limitations. Classical physics explained everyday phenomena before quantum mechanics unveiled a stranger reality. Each breakthrough came from taking anomalies seriously. Cosmologists today stand at a similar threshold. The anomalies might evaporate with better data, or they might herald a transformation in how we understand the universe. Either outcome advances knowledge. Confirming Lambda CDM more precisely would be valuable. Discovering its flaws would be historic. Both possibilities drive researchers forward. The next few years will be decisive. New telescopes are coming online. Existing surveys are gathering more data. The era of precision cosmology is just beginning, and the instruments racing to solve these mysteries span ground and space alike. A fleet of extraordinary machines is scanning the cosmos. Each one brings unique capabilities. Together, they might finally crack the puzzles that haunt cosmology. The James Webb Space Telescope continues its transformative observations. Its infrared vision penetrates dust and distance to reveal the earliest galaxies. Future surveys will catalogue thousands more objects from the cosmic dawn. Each one tests our models of how structures formed. The Vera Rubin Observatory in Chile will soon begin the largest astronomical survey ever attempted. Its camera contains over 3 billion pixels. Every few nights, it will photograph the entire visible sky. Over a decade, it will track billions of objects, including supernovae that constrain the expansion, history, and gravitational lenses that reveal dark matter. The European Space Agency's Euclid telescope launched in 2023. It is mapping the geometry of the universe by measuring how light from distant galaxies bends around intervening matter. This weak gravitational lensing directly probes dark matter distributions and dark energy's influence across cosmic time. DESI continues collecting spectra from its Arizona mountaintop. By the time its survey concludes, it will have measured 50 million galaxies and quasars. The resulting three-dimensional map of the universe will span unprecedented volumes and epochs. The Nancy Grace Roman Space Telescope, planned for launch in 2027, will combine wide-field imaging with precise measurements of supernovae. It will gather enough data to measure dark energy with unprecedented accuracy and cross-check results from other experiments. Ground-based facilities also contribute. The Atacama Cosmology Telescope has mapped the cosmic microwave background with exquisite precision from the Chilean Andes. Its successor, the Simons Observatory, is under construction nearby. Future experiments like CMB-S4 will push measurements even further. Each instrument attacks the problem from a different angle. Webb probes the early universe directly. Rubin surveys the late universe statistically. Euclid measures geometry. DESI tracks expansion. Roman provides independent cross-checks. The cosmic microwave background constrains initial conditions. When results from all these experiments converge, the picture will clarify. If they agree on lambda CDM, the model will be vindicated more strongly than ever. If they disagree, new physics will be implicated beyond reasonable doubt. The timescale for convergence is years, not decades. Data is already flowing. Analyses are underway. The cosmology community watches results from each experiment with intense interest. Some researchers feel we are on the verge of a breakthrough. The Hubble tension has persisted too long to be a simple error. The DESI hints have strengthened rather than faded. The impossible early galaxies keep appearing. Something real seems to be driving these anomalies. Others counsel patience. Cosmology has seen false alarms before. Statistical fluctuations can masquerade as signals. Systematic errors can hide in unexpected places. Extraordinary claims require extraordinary evidence. Both perspectives have merit. The scientific process demands rigor and skepticism. It also rewards attention to persistent anomalies that refuse explanation. The telescopes will eventually deliver verdicts. Until then, cosmologists continue probing the darkness, searching for answers that might reshape everything we know. And at least one Nobel laureate believes we have already reached a point of crisis. Adam Rees shared the 2011 Nobel Prize in Physics for discovering that the universe's expansion is accelerating. He has spent decades measuring the Hubble constant with ever greater precision, and he no longer hedges his words. The discrepancy between the observed expansion rate and the predictions of the standard model suggests our understanding of the universe may be incomplete. Those are his words. Coming from anyone else, they might sound speculative. Coming from a Nobel laureate who helped establish the very framework being challenged, they carry weight. Rees leads the SH0ES collaboration, which has produced the most precise local measurements of the Hubble constant. Using Cepheid stars and supernovae calibrated by the Hubble and Webb telescopes, his team consistently finds values around 73. The uncertainty has shrunk below 2%. Random error cannot explain the gap with Planck's 67. With measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe. Rees offered this assessment after Webb confirmed that the Cepheid distances were accurate. The easy escape routes had closed. The tension was not going away. Other prominent scientists have echoed this concern. At a meeting of the American Astronomical Society in early 2025, Duke University astrophysicist Dan Skolnick declared that the Hubble tension was now a crisis. The word choice was deliberate. Crisis implies urgency. It signals that business as usual will not suffice. What elevates tension to crisis? Several factors combine. First, the statistical significance. 5 sigma is the threshold particle physicists use for discovery. The Hubble tension hovers at this level. If 5 sigma means discovery when physicists find new particles, it should carry similar weight when cosmologists find discrepancies. Second, the persistence. The tension has not faded with better data, it has solidified. Webb strengthened it. Independent methods confirm it. Years of searching for errors have come up empty. Third, the breadth. The Hubble tension is not the only problem. DESI hints at evolving dark energy. Early galaxies appear too massive. The SATE tension suggests matter clusters slightly less than expected. Multiple independent anomalies point toward the same conclusion. Something is missing from our models. Fourth, the stakes. The lambda CDM model is not some provisional guess. It is the foundation of modern cosmology. Textbooks teach it as settled science. Entire research programs assume its validity. If it fails, vast intellectual infrastructure requires rebuilding. Crisis is not a word scientists use lightly. It acknowledges that normal methods have failed to resolve a problem. It calls for new ideas, new approaches, possibly new physics. Some researchers dislike the term. They argue it overstates the situation. The standard model still explains most observations. The anomalies might have conventional explanations not yet discovered. Patience, not panic, serves science better. But Rees and others counter that complacency carries risks too. Ignoring persistent discrepancies delays progress. The sooner the community accepts that something is genuinely wrong, the sooner solutions can emerge. Whether crisis is the right word matters less than the underlying reality. Cosmology faces genuine puzzles that current frameworks cannot resolve. Those puzzles might lead somewhere profound, and their resolution will change how humanity understands its place in the cosmos. We have traveled a long way together, from the Hubble tension to impossible galaxies, from dark matter to dark energy, from Einstein's equations to the edge of what physics can explain. Now step back, consider what all of this means. For most of human history, the universe seemed small and comprehensible. The sky held fixed stars. The cosmos centered on Earth. Time began at creation and would end at judgment. These beliefs felt certain to those who held them. Then came Copernicus, Galileo, Newton. Earth became one planet among many. The solar system became one system among billions. The universe expanded from cozy to incomprehensible. Then came Einstein, Hubble, Penzias, Wilson. Space itself could curve and stretch. The cosmos had a beginning in a primordial explosion. Time was not separate from space but woven into it. Then came dark matter and dark energy. The stuff we can see amounts to mere 5% of reality. The rest is invisible, mysterious, dominant. We are made of the minority ingredient in a universe we barely comprehend. And now the cracks appear. The measurements refuse to match. The models struggle to explain what we observe. The framework that seemed so solid reveals hidden weaknesses. This is not a failure. This is how science works. Every generation builds on the last. Every framework explains more than its predecessor. Every new puzzle points toward deeper understanding. The Hubble tension might seem like a technical disagreement about numbers. It is not. It is a window into physics beyond the standard model. It hints at forces and fields not yet discovered. It suggests the universe is stranger than our best theories can currently describe. If early dark energy exists, the cosmos received an extra kick that shaped everything we see. If dark energy evolves, the fate of the universe is not what we thought. If gravity requires modification, Einstein's triumph needs extension just as Newton's once did. These possibilities are thrilling. They mean there is more to discover. They mean future generations will understand things we cannot imagine. They mean the universe has not surrendered all its secrets. Humanity is young. Our species has existed for perhaps 300,000 years. Our scientific civilization is barely 4 centuries old. The cosmos is nearly 14 billion years old and will persist for trillions more. We have barely begun to understand where we are. The puzzles we face today are gifts. They are invitations to look deeper, think harder, question assumptions. They connect us to generations past, who faced their own mysteries, and to generations future who will face mysteries we cannot foresee. When the James Webb Space Telescope reveals impossible galaxies, it is telling us our imagination was too small. When DESI hints at evolving dark energy, it is telling us the universe is more dynamic than we assumed. When the Hubble tension refuses to close, it is telling us that something profound awaits discovery. We do not know what that something is. We do not know when we will find it, but we know that we are searching. And in that search lies the essence of what makes us human. The universe is vast, it is ancient, it is strange beyond comprehension, and we are the part of it that is waking up and asking questions. That is not a small thing. That might be the most remarkable thing of all. The Hubble tension is not alone. Another discrepancy lurks in the data. Scientists call it the S8 tension, and it points in the same troubling direction. S8 is a parameter that describes how strongly matter clumps together in the universe. Higher values mean matter clusters more tightly. Lower values mean it spreads more evenly. The standard lambda CDM model predicts a specific value based on conditions in the early universe. Here is the problem. When cosmologists measure S8 using the cosmic microwave background and project forward using the standard model, they get one number. When they measure it directly by observing how galaxies cluster today, they get a lower number. Matter in the present universe appears less clumped than it should be. The discrepancy is smaller than the Hubble tension. It hovers around 2 to 3 sigma rather than 5. Statistically, it could be a fluctuation. Many 2 sigma hints have vanished with better data, but it has not vanished. Multiple independent surveys find the same pattern. The Dark Energy Survey, the Kilo Degree Survey, and the Hypersuprime Cam Survey all report S8 values below the Planck prediction. The methods differ. The datasets are independent, yet they agree with each other while disagreeing with the early universe measurement. This pattern echoes the Hubble tension. Early universe observations, interpreted through lambda CDM, predict one thing. Late universe observations measure something else. The model that connects them seems to be missing something. Some researchers dismiss the S8 tension as less severe than the Hubble tension. The statistical significance is weaker. Systematic errors in galaxy surveys are harder to control than in supernova measurements. Perhaps the discrepancy reflects observational challenges rather than new physics. Others see a deeper pattern. The Hubble tension says the universe expands faster than predicted. The S8 tension says matter clusters less than predicted. Both anomalies involve the late universe deviating from early universe expectations. Both suggest the standard model fails to capture something about cosmic evolution. If a single modification to lambda CDM could resolve both tensions, that would be powerful evidence for new physics. Early dark energy is one candidate. By altering the expansion history, it changes both the predicted Hubble constant and the predicted clustering amplitude. Some models can address both tensions simultaneously. Modified gravity offers another avenue. If gravity behaves differently on cosmological scales, it would affect both expansion and clustering. The deviations might manifest as exactly the tensions we observe. Dark matter interactions provide a third possibility. If dark matter particles occasionally collide with each other or with ordinary matter, they would spread out more than standard cold dark matter. This would reduce clustering and lower S8. Each proposal has strengths and weaknesses. None has achieved consensus. But the persistence of the S8 tension alongside the Hubble tension suggests cosmologists should take both seriously. The Dark Energy Survey recently released its final analysis, combining 6 years of data. The S8 value came out below Planck's prediction. The gap widened slightly compared to earlier results. When combined with DESI measurements, the tension with the standard model grew more pronounced. This convergence across experiments matters. If one survey found low S8, it might reflect that survey's peculiarities. When multiple surveys using different methods all find low S8, the signal gains credibility. We are not yet at the point of declaring the standard model broken. The evidence remains circumstantial. Future surveys with larger datasets and better controlled systematics will clarify whether the S8 tension is real. But the pattern is suggestive. Two independent parameters, two independent tensions, both pointing toward the same conclusion. Lambda CDM might be incomplete. And there is yet another method for measuring the Hubble constant that avoids both the cosmic microwave background and the traditional distance ladder entirely. In 2024, the James Webb Space Telescope captured something never seen before. A single quasar appearing 6 times in one image. Scientists called it the first Einstein zigzag, and it might help resolve the Hubble tension. The phenomenon relies on gravitational lensing, one of the strangest predictions of general relativity. Massive objects bend the fabric of space-time. Light passing near them follows curved paths. If a massive galaxy sits between us and a distant quasar, the galaxy acts like a cosmic magnifying glass. It bends the quasar's light around itself, sometimes creating multiple images of the same object. Normally, gravitational lensing produces 2 or 4 images arranged around the lensing galaxy. The Einstein zigzag is different. 2 separate galaxies, nearly perfectly aligned along our line of sight, each bend the light independently. The result is 6 images of the same quasar, arranged in an unusual zigzag pattern. This configuration is extraordinarily rare. Finding it required both precise alignment and Webb's sharp vision, but its rarity makes it valuable. The double lens provides extra constraints that single lenses cannot offer. Here is why it matters for cosmology. Quasars are not steady beacons. They flicker as gas swirls into their central black holes. When a quasar brightens, that brightening appears in each lensed image. But because light takes different paths to create each image, the brightening arrives at different times. These time delays depend on the geometry of the universe. Specifically, they depend on how distances translate into angles and how the expansion rate affects light travel times. By measuring the delays precisely and modeling the mass distribution of the lensing galaxies, astronomers can calculate the Hubble constant. This method is completely independent of both the cosmic microwave background and the traditional distance ladder. It does not rely on Cepheid stars, supernovae, or any of the usual calibrations. It uses geometry and timing alone. Previous time delay measurements using simpler lens systems produced Hubble constant values around 73, consistent with local measurements and in tension with Planck. The Einstein zigzag promises even better precision because the double lens configuration constrains the geometry more tightly. The team that discovered the zigzag is already working on detailed models. They expect to extract a Hubble constant measurement with smaller uncertainties than single-lens systems allow. If the result confirms 73, it will strengthen the case that the tension is real. If it produces a different value, that would be equally interesting. It might reveal systematic errors in other methods or point toward even more complex physics. Gravitational lensing offers other cosmological probes as well. The way light from distant galaxies gets subtly distorted by intervening dark matter reveals how that dark matter is distributed. These weak lensing measurements constrain both the amount of dark matter and the strength of clustering, connecting to the S8 tension. The Euclid Space Telescope is mapping weak lensing signals across vast swaths of sky. Its data will provide independent checks on both the Hubble constant and the clustering amplitude. Combined with DESI, Webb, and ground-based surveys, a comprehensive picture will emerge. Each method attacks the problem from a different angle. Each carries its own systematic uncertainties. When multiple independent methods converge on the same answer, confidence grows. When they disagree, new puzzles emerge. The Einstein zigzag represents the cutting edge of this multi-pronged approach. It exploits rare cosmic alignments to extract fundamental parameters with minimal assumptions. And it reminds us that the universe still holds surprises waiting to be discovered, but some surprises are closer to home, including stars in our own galaxy that seem impossibly old. There is a star in our galaxy that appears to be older than the cosmos itself. This is obviously impossible, yet the measurements persist. The star is called HD 140283, nicknamed the Methuselah star. It lies about 190 light-years from Earth, close enough for precise observations. Its composition marks it as ancient. Almost no heavy elements contaminate its atmosphere. Only hydrogen, helium, and traces of heavier atoms forged in the earliest generations of stars. Based on its brightness, temperature, and composition, astronomers estimate Methuselah's age at around 14.5 billion years. The uncertainty spans several hundred million years in either direction. But even the lower bound pushes uncomfortably close to the accepted age of the universe, 13.8 billion years. Stars cannot be older than the universe that contains them. Something must be wrong. Either the stellar age estimate is off, or the cosmic age estimate needs revision. Stellar ages carry significant uncertainties. They depend on models of how stars burn fuel and evolve over time. Different assumptions about convection, nuclear reaction rates, and initial compositions produce different ages. The error bars on Methuselah's age are large enough that it might comfortably fit within a 13.8 billion-year-old cosmos. But here is where the Hubble tension enters. The cosmic age of 13.8 billion years comes from the Planck measurement of the Hubble constant. A lower expansion rate means a longer time since the Big Bang. If the Hubble constant is actually around 67, the universe is old enough to accommodate even the oldest stars. But what if local measurements are correct? What if the Hubble constant is really 73? Then the universe is younger, closer to 13 billion years old, and Methuselah becomes genuinely problematic. A 13 billion-year-old universe cannot contain a 14.5 billion-year-old star. The stellar models would need revision, or the star's distance and properties would need reinterpretation. Neither option is impossible, but neither is comfortable. This is another way the Hubble tension connects to fundamental questions. The age of the universe is not an abstract number. It constrains what can exist within it. Stars, galaxies, and structures all require time to form. If the timeline shrinks, the constraints tighten. Other ancient stars exist throughout the galaxy. Globular clusters, dense swarms of old stars orbiting the Milky Way, contain populations nearly as ancient as Methuselah. Their ages cluster around 12 to 13 billion years. Most fit within the standard timeline. A few push the boundaries. Improved measurements from the Gaia spacecraft have helped refine stellar distances and therefore ages. The uncertainties have shrunk but not vanished. Methuselah's age remains uncomfortably high even with the best modern data. Some researchers argue this is merely a calibration issue. Stellar models might systematically overestimate ages for metal-poor stars. Better physics might bring the estimates down. Others see a genuine puzzle. If multiple ancient stars cluster near the cosmic age limit, perhaps the limit itself is wrong. Perhaps the universe is older than Planck implies. Perhaps something about the early expansion history differs from standard assumptions. Early dark energy could help here too. By changing the expansion history, it could make the universe effectively older from the perspective of structure formation. Stars would have more time to form without the cosmic age exceeding reasonable bounds. The oldest stars are fossils from the cosmic dawn. Their existence constrains both stellar physics and cosmology. Every improvement in measuring their ages ripples outward into fundamental questions about the universe itself. And speaking of the cosmic dawn, One proposed solution to the early galaxy problem involves objects that might have formed even before the first stars. What if black holes did not need stars to form? What if some of them arose directly from the chaos of the early universe? This idea, called primordial black holes, has circulated for decades. Recently, the impossible early objects discovered by Webb have given it new urgency. The standard story of black hole formation goes like this. Massive stars burn through their fuel and collapse, their cores crush down into singularities. Black holes are born from stellar death. But stellar mass black holes start small. Growing them into the supermassive monsters that power quasars requires time. They must consume vast amounts of gas. They must merge with other black holes. Each step takes millions or billions of years. The early universe did not have billions of years. When Webb sees supermassive black holes existing just 5 or 600 million years after the Big Bang, the standard timeline strains. There simply was not enough time for normal growth. Primordial black holes offer an escape. If some black holes formed directly in the first moments after the Big Bang, they could have started much larger. Density fluctuations in the primordial plasma might have been extreme enough in some regions to collapse immediately into black holes. No stars required. These primordial seeds could have weighed thousands or even millions of times more than our star from the very beginning. With such a head start, reaching supermassive scales by the epoch Webb observes becomes plausible. The idea has testable consequences. Primordial black holes would have affected their surroundings in specific ways. They would have influenced the cosmic microwave background through their gravitational effects. They would have generated gravitational waves when they merged. They might even constitute some or all of the dark matter. Searches for these signatures have produced mixed results. Some studies claim hints of primordial black holes. Others set stringent limits on their abundance. The parameter space remains partially open but increasingly constrained. If primordial black holes exist, they would reshape our understanding of the early universe. The density fluctuations needed to form them would require modifications to inflationary models. The physics of the first fraction of a second after the Big Bang would need revision. Webb's discoveries do not prove primordial black holes exist, but they make the idea more attractive. Every impossibly massive early black hole that defies conventional growth models adds motivation to consider unconventional origins. Alternative explanations exist. Direct collapse black holes, formed from pristine gas clouds that never fragmented into stars, could also provide massive seeds. Super Eddington accretion, where black holes feed faster than the theoretical limit by shrouding themselves in thick gas, might accelerate growth. Each alternative has its own challenges. Direct collapse requires special conditions that might be rare. Super Eddington accretion cannot be sustained indefinitely. Primordial formation requires exotic early universe physics. The truth might involve combinations. Perhaps some early black holes formed primordially, while others grew from direct collapse. Perhaps different environments favored different pathways. The diversity of early objects, Webb observes, might reflect a diversity of formation channels. Untangling these possibilities requires more data. Gravitational wave observatories like LISA, planned for launch in the next decade, will detect mergers involving massive black holes across cosmic history. Their signals will reveal the masses and origins of these objects directly. Until then, primordial black holes remain a tantalizing possibility. They represent one more way the early universe might have been stranger than our models assume, and all of these early structures exist within a grander architecture that dark matter built. Zoom out far enough, and the universe reveals a hidden pattern. Galaxies do not scatter randomly through space. They arrange themselves along vast filaments, connected at nodes, surrounding enormous empty voids. Scientists call this structure the cosmic web. The web stretches across billions of light years. Its filaments contain thousands of galaxies strung like pearls on invisible threads. Its nodes host massive galaxy clusters where filaments intersect. Its voids span hundreds of millions of light years with almost nothing inside. This structure did not arise by accident. It grew from tiny seeds planted in the first moments after the Big Bang. Quantum fluctuations during inflation created microscopic density variations. Over billions of years, gravity amplified these variations. Denser regions pulled in more matter and grew denser still. Less dense regions emptied out and became voids. Dark matter drove this process. Because it interacts only through gravity, dark matter began clumping before ordinary matter could. It formed the scaffolding, along which gas later flowed, and stars eventually formed. Galaxies trace dark matter, like cities trace rivers. The cosmic web is not just visually striking. Its structure encodes cosmological information. The typical spacing between filaments depends on the expansion history and the properties of dark matter. The sizes of voids constrain how quickly structures grew. The clustering of galaxies at different epochs reveals how dark energy influenced evolution. DESI exploits this information directly. By mapping millions of galaxies, it traces the cosmic web in 3 dimensions across billions of years. The patterns it measures, called baryon acoustic oscillations, act as standard rulers for cosmic distances. These rulers reveal how fast the universe was expanding at different times. The weak lensing surveys from Euclid and the Rubin Observatory probe the web differently. They measure how foreground dark matter bends light from background galaxies. The distortions reveal the distribution of mass, including the invisible dark matter that dominates filaments and clusters. Together, these measurements constrain cosmological parameters with extraordinary precision. They test whether lambda CDM correctly predicts the growth of structure. They search for deviations that might signal new physics. The S8 tension emerges from exactly these measurements. The cosmic web appears slightly smoother than the standard model predicts. Filaments are a bit less pronounced. Voids are a bit less empty. Something seems to have suppressed the growth of structure compared to expectations. If dark energy evolved over time, it would have affected structure growth differently than a constant cosmological constant. If dark matter has unexpected properties, it might cluster differently. If gravity weakens on large scales, structures would grow more slowly. Each possibility leaves fingerprints in the cosmic web. Future surveys will map the web with unprecedented detail. The Rubin Observatory will catalogue billions of galaxies. Euclid will measure shapes for over 1 billion. DESI will continue gathering spectra until it reaches 50 million objects. The combined dataset will reveal the web's structure with exquisite precision. Any deviation from lambda CDM predictions will stand out clearly. Either the standard model will be confirmed with new confidence, or cracks will widen into undeniable fissures. The cosmic web is both beautiful and informative. It displays the universe's large-scale architecture while encoding clues about fundamental physics. Every filament and void carries messages from the early cosmos, waiting to be decoded. And decoding those messages might happen sooner than many expect. We stand at a remarkable moment. The puzzles are clear. The tools are ready. The next 10 years might transform our understanding of the universe. Consider what is coming. The James Webb Space Telescope has only begun its mission. Its initial observations revealed surprising early galaxies and mysterious little red dots. Future deep surveys will expand these samples from dozens to thousands. Statistical patterns will emerge. Anomalies will either multiply or resolve into conventional explanations. Webb will also target specific puzzles directly. Follow-up spectroscopy of the strangest early objects will reveal their true nature. Are they galaxies with impossible stellar masses? Or black holes mimicking stellar light? Are the little red dots a transient phase? Or something entirely new? Answers are within reach. The Vera Rubin Observatory will begin operations within the next year. Its 10-year survey will photograph the entire southern sky repeatedly. Billions of galaxies will be catalogued. Thousands of supernovae will be discovered and tracked. The resulting dataset will constrain dark energy and the Hubble constant with unprecedented statistical power. Euclid is already collecting data from its orbit around the second Lagrange point. Its weak lensing maps will reveal dark matter distributions across 10 billion years of cosmic history. Its measurements of galaxy clustering will test lambda CDM predictions for structure growth. First cosmological results are expected within 2 years. DESI continues observing from its Arizona mountaintop. By the survey's end, it will have mapped 50 million objects. The baryon acoustic oscillation measurements will tighten constraints on evolving dark energy. Either the hints will solidify into discovery, or they will fade as statistical flukes. The Nancy Grace Roman Space Telescope launches in 2027. Its wide-field infrared camera will survey supernovae with precision rivaling Webb. It will measure distances and expansion rates across a huge volume of space. Cross-checks with other experiments will reveal any hidden systematic errors. Ground-based cosmic microwave background experiments are also advancing. The Simons Observatory is under construction. CMBS-4, a next-generation array of telescopes, is planned for the early 2030s. These instruments will measure the microwave background with sensitivity far exceeding Planck. They will search for signatures of primordial gravitational waves, early dark energy, and other new physics. Gravitational wave astronomy will contribute as well. The LISA space mission, planned for the mid-2030s, will detect mergers of massive black holes across cosmic history. These signals will reveal how supermassive black holes formed and grew, testing models of early structure formation. All these datasets will be analyzed together. Tensions between experiments will either sharpen or disappear. Consistent deviations from lambda CDM will demand new physics. Consistent agreement will confirm the standard model more powerfully than ever. The timescale for resolution is years, not generations. The questions that trouble cosmology today might have answers by the early 2030s. Scientists currently working on these problems might live to see their resolution. This is rare in fundamental physics. Many questions span careers or even centuries. The age of the universe, the nature of dark matter, the properties of dark energy. These seemed like problems for future generations. Now they feel tantalizingly close. Of course, nature might surprise us. New puzzles might emerge even as old ones resolve. The history of science teaches humility. Every answer spawns new questions. But the trajectory is clear. We are entering an era of convergence. Multiple independent experiments, using different methods, will confront the same questions simultaneously. Agreement or disagreement will be unambiguous. The standard model will stand or fall on evidence, not speculation. Whatever happens, the next decade will be extraordinary. Science moves in rhythms, long periods of steady progress punctuated by sudden transformations. We might be approaching one of those transformations now. The signs are everywhere. Multiple tensions between theory and observation. Persistent anomalies that resist conventional explanation. New instruments revealing surprises faster than theorists can absorb them. A growing sense among researchers that something fundamental is shifting. Not everyone agrees. Some see the current puzzles as normal scientific messiness. Data is noisy. Measurements carry uncertainties. Tensions come and go. The standard model has survived challenges before and will survive this one. This view deserves respect. Caution protects science from chasing phantoms. Many apparent anomalies have evaporated under scrutiny. The history of cosmology includes false alarms that seemed compelling at the time. But history also includes genuine revolutions, moments when accumulated puzzles suddenly coalesced into new understanding, when the old framework broke and a better one emerged. The Copernican revolution transformed humanity's place in the cosmos. The Einsteinian revolution transformed our understanding of space, time, and gravity. The discovery of the expanding universe transformed cosmology from speculation into precision science. The discovery of cosmic acceleration transformed it again, Each revolution was preceded by tensions, observations that did not fit existing frameworks, anomalies that resisted explanation, a growing unease among experts that something was missing. The current situation has that flavor: the Hubble tension, the S8 tension, the impossible early galaxies, the hints of evolving dark energy. Individually, each might be explained away. Together, they paint a picture of a framework under strain. If revolution comes, what might it look like? Perhaps early dark energy will be confirmed. A fleeting burst of cosmic acceleration in the first 100,000 years would reshape our understanding of the early universe. It would connect particle physics to cosmology in new ways. It would demand explanation in terms of fundamental fields not yet discovered. Perhaps dark energy really is evolving. A dynamic component rather than a static constant would require entirely new theoretical frameworks. It might connect to string theory, quantum gravity, or physics beyond the standard model of particles. Perhaps gravity itself needs modification. General relativity might be an approximation that fails on cosmological scales. A deeper theory might unify gravity with quantum mechanics while explaining the anomalies we observe. Perhaps something entirely unexpected awaits. History's greatest revolutions were not anticipated. They came from directions no one was looking. The next breakthrough might emerge from an observation not yet made or a connection not yet drawn. Whatever happens, the process will be thrilling. Anomalies force creativity. Tensions demand resolution. The pressure of unexplained observations drives science forward. We are privileged to witness this moment. The questions being asked today are among the deepest humans have ever posed. What is the universe made of? How did it begin? How will it end? What laws govern its evolution? These questions once belonged to philosophy and religion. Now they belong to science. And science is closing in on answers. Not final answers. Science never claims finality, but better answers, deeper answers. Answers that will seem obvious to future generations even as they seem miraculous to us. The James Webb Space Telescope peers into cosmic dawn and finds surprises. DESI maps the expansion history and finds hints of change. Theorists propose ideas and observers test them. The cycle continues as it has for centuries. Somewhere in this cycle, revolution waits. Perhaps it is already underway, visible only in retrospect. Perhaps it lies just ahead, one crucial observation away. Either way, the search continues, and that search, more than any particular answer, defines what it means to be human. We are the universe examining itself, asking questions, seeking understanding, standing at thresholds and daring to cross. That is not just science. That is who we are.